This lecture is on the second part on the properties of the DTFT. In this lecture, we will continue our discussion on the properties of the DTFT, and specifically, we will focus on upsampling and downsampling, and we will go over a few examples that apply these properties. Upsampling and downsampling are properties or operations that are done in signal processing to stretch or squeeze a discrete signal. And maybe it's best explained through an example. So if you look at the example of the signal here, this signal here, right? So you can see it has value A at 0, value B at 1, and so on and so forth. Now if I upsample, then what I do is that I stretch out the signal. So I'm sampling more of the signal, but since I don't have more information to fill the signal with more samples, then what I do, I add zeros in the places where I don't know what the values are. So for example, if this was a continuous signal, then upsampling would be would contain more information. So if I'm sampling this signal, let's say every, I don't know, time unit, then if I do upsampling, then I can just introduce more samples in the middle, right? So I can always introduce extra samples. But here, because I don't have the information, I only have access to the discrete signal, so what I would introduce, I will introduce more samples, but they are equal to 0. So in some sense, I'm stretching out the signal. One thing is that here, the sampling factor is equal to 3 in this case. So, and I mentioned this in the lecture on the Z transform. So if we're upsampling by a factor n, this means I'm introducing n minus 1 0 values. And for downsampling, it's the inverse operation. So what I'm doing is, if I'm downsampling by a value of 2 here, this means I'm removing one sample in the middle. So to get the upsampled version or the downsampled version, a factor 2, I have to kill every other signal, and you obtain this guy. So if you if you're downsampling, let's say with a factor, let's say 3, then you have to kill every 2 signals. So you have to jump 2 signals. So you have to. So this would be n equal to 3. So this is the upsampling, and this is a easy description of the upsampling and the downsampling. And usually in a diagram we represent the upsampling by this box with an arrow going up, and next to it the factor of the upsampling, or the downsampling the other way. And since it's the upsampling is a stretch of the signal, so y of k, the upsampled version, is x of k by n, and in the downsampled version, y of k is x of k times n. And here I have written in more details the formulas for the upsampled and downsampled signals. So if you're a little bit confused, I can do a little example to show you why. So let's suppose you have this signal here. Let's suppose this is x of k, which is 1 at 0, and let's suppose it's 1/2 at 1, and then 1 again, let's suppose, at 2. Then if I downsample, or if I upsample by a factor of 2, this means I have, so this is x of k, or x of n, then y of k, the upsampled version is going to be this one. So at 0 is 1, at 1 is 0, and at 2 is 1/2. And then you have a value that is 0, and then at 4 you have 1 again. So that's the upsampled version. Now, the value of y of 0 here is equal to x of 0, right? So meaning, and then y of 1 is equal to, or y of 2 is equal to x of 1, and y of 4 is equal to x of 2, and so on and so forth. Because what you're doing here is that, what these equations are saying is that this guy is here, and this guy 2 here is 1, and this guy is here. So the multiples, so the values of the x's are mapped to the multiples of n at the y's. So 0 is to 0, 1 to 2, and 2 to 4. Here I'm upsampling by a factor of 2. And this is why y of k is x of k by n if k mod n is equal to 0. Otherwise it's 0. So otherwise all the values in between are 0. And again, also you can double check that this formula for the downsampling also makes sense. So for downsampling, we're not going to spend much time on it right now because for a discrete signal, when we downsample, we lose values, and it's not clear how we can find a relationship between the DTFT of the original signal and the DTFT of the downsampled signal. But the story is different for upsampling. So the formula for upsampling is that the upsampled version of the signal, so this guy here is upsampled with factor n, and then the formula says that the DTFT of y of n is the DTFT of x, but where instead of having omega, you stretch omega by a factor of n. So it's x of ej omega times n. So so what's happening? Actually, you're squeezing the omega axis, the frequency axis, by a factor of n. So in the previous example where I upsampled by a factor of 2, and the frequency domain, what I will be doing is I will be squeezing the frequency axis, the omega axis, by a factor of 2. So the stretching in the time domain corresponds to a squeezing in the frequency domain. 6. Let's apply what we learned so far to find the DTFT of the following signal. And this signal is 0 outside the interval 0, 12. So everything here is 0, and everything here is 0, and for the values between 0 and 12 you have value 1 and then you go to 0, and then value 2 and then you go to 0, and so on and so forth. Now, how can we find the DTFT of this signal? Let's try to relate it to things we know from before. So this looks a little bit like a box signal. So if you remember, a box signal would be something like this. Let's say centered around 0. And here, so I would have so -1, -2, -3, and +1, 2, and 3. Since the original signal has 7 impulses, right? So this is the box signal here, and everything outside is 0. So so the way I can go from this box to this signal is first shifting the box to the right by 3 steps, and then upsampling. So again, so the way I can do it is by first shifting the box 3. So if I do the shift, so time shift, so instead of the box being here, the box would start at 0 and would end at 6. And then what I do is, again, and next I would upsample by a factor of 2. So I will explain these steps in details in the coming slides, but the first thing to keep in mind here is that this signal that I care about can be obtained by few operations that are done on the box signal or the rectangular signal. And this is the box signal that I talked about. So it's a box between -3 to 3, and it has value 1 in this interval, and it could be written, so here it's designated by the signal z of n, and it's equal to un plus 3 minus un minus 4. So why is it that way? Because if you take un plus 3, it's a step function that is starting at, it's shifted to the left. So this is 0, -1, -2, and -3. So it's a step function that's shifted to the left. So it starts at here, right? And you have 1, 2, 3. And now you want to kill everything starting 4. So you want to kill everything starting here, but you want to keep the 3. So this is why you have to subtract the following step function. So you want to subtract this step function here. No, sorry, that's not it. So you have to, let me fix it. So you have to, because you have to keep the 3 here. So, so this is un plus 3. And now you need to subtract all the values, including 4, and including and larger than 4. So let me do this in blue here. So you need to subtract this this step function. So this is un minus 4. And then what you get in the end is the thing that I'm going to highlight in red. So you're going to get this part, this part, this part, and then this part. And then you're going to get the box signal. Let's find now the DTFT of this box signal that starts at -3 and end at +3. So let me draw it again here so you can see it. So we're trying to find, it's a discrete version of this guy here. So right, so we can do it by just applying the formula, and then I have the sum from n equal to -3 to +3, x of n, or z of n, e minus j omega n. So let me fix these typos here. So this is z, since I call the signal z, and here there's no capital N. And then what I would have here is, so it's the sum of here, the sum from n equal to -3 to +3, because it's the signal is equal to 1, so it's equal to the sum from -3 to 3, 1 times e minus j omega n. And this part here is also a typo that you should not worry about. And then this part here is geometric series. It starts at n equal to -3. So I'm just going to apply the formula. So let me remind you, the formula is the following. So maybe I can write it down on the left here. So if you have the sum, which is let's write it as a plus or let's say a plus a square plus a cube plus so here a to the power 1 plus a let's say capital N. So you stop at n terms. Then the sum of this is equal to the first term, which is a, first term and the sum, 1 minus a to the number of terms, and here is equal to n divided by 1 minus a. So it's going to be equal to a 1 minus a capital N divided by minus a. So the reason I like to think of it as first term 1 minus a to the number of terms, because sometimes you start with 0 here and then you're confused whether you want to add 1. So it's a to the number of terms. So now if I apply it here, the first term is obtained by plugging in n equal to -3. So this will give you E3J omega, and then 1. And now how many terms I have in the sum? I have 7 terms. So right, so I have three negative terms and 3 positive terms and the 0. So it's going to be 1 minus E minus J 7 omega divided by 1 minus E minus J omega. And now if I do the calculations, I will get, and use Euler formula, I will get the following formula. So this is equal to the Z transform of this box function. It's sine of 7 omega by 2 divided by sine of omega by 2. And this is how it looks like when you plot the DTFT of the box function. So it's the equivalent of the sinc function, if you want to think of it this way, but it has to be periodic because it's a DTFT. So this is how it looks like. Let me make a short break here and suggest a problem to do by yourself. I usually suggest these problems at the end of the slides or the lecture, but I'm going to do it here because it's very related to what I just did before. So the problem to do yourself is the following. Prove that the following box signal, and it looks like this. So it's a box signal that starts at -n and goes from the interval from -n to +n. And the question is to find the DTFT of this signal. And to help you, I'm giving you the result. And the question, the answer is that to prove that the DTFT looked like something like this. And if you can, you can easily notice that it looks very similar to what we did before, to the signal before. So the signal before, the box started at n equal to 3. And then if you plug in n equal to 3, you get the result from before. And the question here is to derive the general formula of the DTFT of a box signal. And the steps are exactly what we did before. So all you have to do is just follow the same steps. And again, the takeaway message of here is that the box signal in the time domain is this function here that looks like the sinc signal. Now that we found the DTFT of the box signal, let's come back to our example, which was to find the DTFT of this signal here. And recall that the way we wanted to do it is by first shifting the box signal to the right by 3 units and then doing the upsampling. And that's what I want to do next. And the operations that we needed to do are the following. First, so we have Z of n, which is the box. So Z of n looks something like this. And then when you delayed by 3, you shifted by 3 to the right, so you'll get Y of n, which is this guy here. Going from 0 to 6, right? And then when you downsample, you get the signal that we care about. So you get 0 and then 1 at 0 and you have you should have 7 pulses. And then you have the extra samples in between. So that's how I'm gonna get the DTFT of this guy from this guy. So first I'm gonna apply the formula of the delay, and then the formula of the upsampling. And recall that since I'm upsampling, then in the frequency domain I'm actually squeezing the spectrum of the signal. So the box has the following DTFT, which is sine 7 omega by 2 divided by sine omega by 2. Now when I shift it by a value of 3, it's equivalent in the frequency domain to multiply by e minus j 3 omega. And again, 3 here is because I have a delay by 3, and if you don't remember where this comes from, please go back to the formula of the time shift. So time shift in the time domain equal to multiplying by the complex exponential here. And now if I do the upsampling, then I have to replace omega in the formula by omega. Upsampling, I have to replace omega by 2 omega here. So I get this formula. So I will have e minus j 6 omega sine 7 omega divided by sine omega. And here you can see in red, I plotted both the DTFT of both signals, the original one and the sampled one. So but you can see how the blue one is the original signal. So in blue is the original signal, as I say here, and then you can see in red how the w-axis is squished.